All right, welcome back. And today we are going to be talking about a problem called non-decreasing array. Now, I really like this problem because a lot of the times people focus too much on like super hard problems or like medium to hard problems and thinking that they need complex data structures and stuff like that. But in the end, you shouldn't really use that many complex data structure. Usually you don't need to do it. It's more about finding creative ways or understanding the problems very well and then implementing it. Usually the difficulty is not implementing it. If you're still having trouble implementing solutions, like imagine if they already tell you what the solution is, and you still have problems implementing it, then you probably have to get better at just normal coding. And then the rest of the part is to try to think of like being very clever and understanding the question and figure out what kind of like data structure or what kind of algorithm can solve that. Let me show you what I mean here. So in this question, it says, given an array with n integers, your task is to check if it could become non-decreasing by modifying at most one element. So basically what this means is make sure that it's monotonically increasing. So let's look at a question. Let's go to the iPad. I actually like to draw a graph usually for this because it helps me explain the question a lot better. So here it says, like imagine if I have a graph. So I have 4, 3, 2, 1. So here I have 4, 2, 3, which is equivalent of this, and then 2, and then 3. So as you can see, it is not monotonically increasing. Monotonically increasing looks like this, right? It's always up, up, up. It never goes down. Once it goes down, it is not monotonically increasing. So the question is, can we turn this graph changing one point, either this one, that one, or this one, so that it's monotonically increasing? And the answer is yes, because we can bring the first point down here. So then it'll become monotonically increasing, right? So then it'll become like that. So which is kind of similar to taking 4, 2, 3 and transforming into 1, 2, 3, right? So that's like the intuition behind this problem. Now, how do we solve this? Okay, imagine given more numbers. Now I'm not even gonna write the numbers. I'm gonna show it to you in terms of points. If we have something like this, 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 so then it looks like this. And then it goes down here. Oops, like this, goes down, goes up, goes up, goes down, goes up. So this can be represented by numbers like, for example, 1, 2, 3, and then back to 0, 4, 5, and then back to 4, and then 6 or something like that. That's kind of equivalent to what I drew the graph here. So the most important thing is understanding that you want to have not a straight line, but a line that keeps going up. So what are the parts that goes down? Well, you see there's this one. Oops, let me put red. There's this one, which is because of this number, and then there's this one, which is because of that number. So how can we fix it? Well, we have to fix this guy to go here so that it would work, or here so that it would work. However, that's 2 fixes. And in this question, we only want 1, right? So let's think about the brute force. How would we do that? One way to do it is to go through your whole array. So imagine if you have this array, and then every time we change the number to be the smallest that it can be, so that it's still monotonic increasing. Like for example, this one, I could change it to, I don't know, negative infinity, or the second one, I could change it to here, and then to see if it's still monotonically increasing, right? And then usually you could either increase or decrease the number. And then what we do is that after we iterate through the whole array and always decreasing by its minimum value, and the minimum value would be changing it to whatever is the previous one, right? So for example, here, if we want to fix it, we go all the way here, so that now it's monotonically increasing. Or here, you go all the way here. So what you do is you go through your whole array of numbers, and then you turn the number you're at now to be equal to the previous number. And then every time you turn that number into the previous one, you call like a function called, is it still monotonically increasing, right? So that would work, because once you realize that it's monotonically increasing, that means after you change one element, it is monotonically increasing. So that would give you true. So that means we would have to loop through the array once, which is O of n. Like I'm talking about the time complexity now. And then for each time you change a value, you have to call, is it monotonically increasing, which takes the whole array and checks if it's monotonically increasing. How do you do that? You check the previous number to see if that number is smaller than yourself, smaller or equal than yourself. So it'd be O of n times O of n, which gives O of n squared. However, this is the brute force way of doing it. The other way of doing it is trying to think about the problem and trying to understand it clearly. So what I mean by that is, if you think about it, whenever there's a graph or a bunch of numbers, then you know that you want a graph that can be changed at most once, right? Imagine we have this, we have that. Let me give you a few examples. Like a great way of doing these interview problems is do a few examples and see if you understand, and then see if you could come up with an algorithm, right? So we definitely know that this graph is definitely possible, because you just have to change this one here, right? But then if your graph looked like this, you know it's impossible, because you could only change one node. You can only change one node. So as long as there's two dips, you see how many dips there are 2 dips here. If there are 2 dips, it's just impossible. You just can't do it, right? However, and then there's a different kind of dip. What if the dip looks like this, right? 1, 2, 3, oops, and then like all the way up. Imagine if your dip looks like that, right? Then yeah, there's 2 dips, like I said again, so that would be not possible. So as long as you have 2 dips, and what does a dip mean? It means that if this number, the previous number is actually bigger. If that happens more than 2 times, it's impossible. So we got that one rule, right? Let's write it down. If 2 dips, then it's false automatically, right? And then what happens if there's 0 dips? Yeah, so remember, we have this rule now. This is for sure, if and only if. And then what happens if there's no dip? It keeps increasing, right? That means every time I look at a number, the previous number is always smaller or equal, right? This one, it's always equal. What does that mean? It means it's true no matter what, okay? If 0 dips, it's gonna be true. Perfect. So yeah, so always break down these problems into different scenarios. Usually if you're too confused or you have no idea where to start, then a very good way of doing it is breaking down. Let me draw it here actually. Let me draw 1 dip. Now if we have 1 dip, meaning that there's 1 over here. Okay, let's draw a dip like this. Right, this is one scenario. Can we fix this? Let's see. Now we want this one to be at least here, right? Because you have to satisfy the fact that the previous one is smaller. But then your next one is gonna be way too small. So that doesn't work, right? So let's remember that. Let's do an X here. No. And then let's draw another one where there is a dip, all right? So is this possible? Yeah, because if you just move it here, it works. It becomes monotonically increasing. So this becomes yes, right? So what's the biggest difference between these two? The biggest difference between these two is that when the dip happens, the previous node is smaller than the next node, right? So that's the difference. And then here, when the dip happens, the previous node is smaller or yeah, smaller in size than the previous node. So in that case, it becomes yes. Also, just to mention, to see the dip, what you usually do is you want to see, okay, I am this node, and then is the following node smaller than me? If it is, then it means, you know, you spotted a decline. So there's multiple ways to spot a decline, right? The first way is like in the beginning when you spot a decline, and then yeah, like something like this, right? Or like that. So in that case, if there's only one decline, like we already said before, if there are two dips, it's always false no matter what. If it's 0 dips, it's always true. And then if it's 1 dip, it depends, right? Like for example, this dip. Like for example, this dip, it's a no, this dip, it's a yes. And then if the dip is on the edge, then what that means is it's always yes, because you can always go infinite down. So no matter what, since you're the first node, you can go infinite down. That's great. And then the other case, I need to draw more. The other case is if you start and then the last one dips, right? So then this is your node, or like your dot. Let's just call it a number. This is your num. And then this dot is there. So is this case possible? Yes. And the reason why is because we can move this up to infinity no matter what, right? It's kind of the same thing as this one, but it's the opposite. You can move it to infinity. Okay. Let's think of other cases. So we thought about these cases. So in this case, what we saw is that, the reason why it doesn't work is because let's call this index, IDX. And then IDX plus 2, let me zoom in. Yeah, IDX plus 2 is smaller than IDX. And then because of that wouldn't work. So then that doesn't work. That's because we cannot change IDX plus 1, which is this one. We cannot change this so that it's still monotonically increasing, right? So let's look at another example. What if, let's see, it's very on the bottom, and then we have IDX here, and then it shoots all the way here. So in this case, this actually works too. And the reason is because IDX minus 1 is smaller than IDX, is smaller or equal to, is smaller than equal to IDX plus 1. IDX minus 1 is this one. Let me put some colors. Oops. So like this is here. And then also, let's do some red. Red is here, right? Because the reason why you can do this is because you can move this down here, right? So here you move down. Wait, let me put a yes here. Yes. Yeah, so here's the case. Let's think back of the case. Here it works because we are right on the edge of the end. And then here it works because it's edge beginning. So no matter what you begin, you could go infinite down. No matter what you do here, you could just go infinite up, right? And then here, the reason why you can do it is because you could bring it down so that it's equal. And then here, in this case, what you can do is you could bring it up. So the faulty node, you could bring it up, and then here you could bring it down. And then that's pretty much all the cases, because what can you do with a single point? You can either bring it up or down or stuff like that. So basically that's pretty much all the cases, and anything that does not, everything that's either not one of these 4 cases will not work, right? Because like I said, you could either bring the node down or up, and then there are different cases for that. And then these are all the cases. Everything else, you could try everything else. Imagine not satisfying these ones. Like for example, this one, you could say that this is the IDX. Like in this no case, this is the IDX, right? Is IDX minus 1 bigger than idx plus 1? No, it is not. Okay, what about this? Is idx bigger than this one? Still a no. So any times you don't satisfy any of these constraints, right, this one, and then idx is smaller than idx2, which means that this one, idx, is smaller than this one, idx plus 2, right? This one is smaller than this one. All right, cool. So enough of this talking. Let's just go back to our rules. So remember we had these two rules, and then we have one more. If one dip, true if satisfy the 4 rules. Either one of the 4 rules, right? Either, true if one of them is true. And then it's either idx equals 0 or idx equals the end minus 1, or let's see, or idx smaller or equal to idx plus 2, or idx minus 1 smaller than idx, right? And there you go. These are the rule. And then we basically write this logic into our code. All right, so let's write it down. So we look at the iPad. We first have to initialize this index. And then first we initialize it to none, because we don't know if there is if there's a decreasing edge. And how do you find a decreasing edge? Well, you have to loop through the whole thing. And then we loop through until, not to the end, but the one before that, because we always have to look to the forward number to see if it decreased or not. So if nums, if like myself is bigger than the next one, then if that's the case, then we put that index into idx, which is the one we cared about. But if it already has something, it means it's not null, then we return false already. That is the case where if we have 2 or more dips. And then if there's no dip, then we just assign it to I, right? So the moment we see 2 dips, we're gonna say false. Okay, so once we get to here, if we don't have anything, that's 0 dips. We remember if it's 0 dips, then we return true, right? Or this is, if it's now the case is, wait, actually let me write it down. If there's only 1 dip, let me write this down. If there's no dip, if there's 2 dip or more, right? And then if there's only 1 dip, there are 4 cases. So if idx is in the beginning, then that's good, because we can do that. We can just decrease it. If idx is at the end, which is nums minus 2, yeah, then we return true also, right? Like, so the reason why it's minus 2 is because minus 1 would be the last element. We care about the one before that. And then what's the other cases? Remember, if idx is smaller or equal to nums idx plus 2. If we looked at our iPad, that's what it says, and return true. And then what's the other case? Well, you can write this cleaner with like one if statement, because you could do or, bunch of or statement, but I'm doing it like this so it's easier to understand. And then idx minus 1 smaller than nums idx plus 1, return true. And if all of these are false, then you get to here. Then you just return false. All right, beautiful. Okay. Oops. So we're gonna run the test now, and okay, the test works, and then we'll submit it. And yeah, the submission works, so that's perfect. So yeah, that's pretty much it for, what is the question called? A non-decreasing array. And yeah, I hope you learned something here, and see you in the next one.